James Clerk Maxwell was born on June 13, 1831 in Edinburgh, Scotland, into a family that valued intellect, learning, and scientific curiosity. His father, John Clerk Maxwell, was a man of deep intellect and steady character, a landowner who also had a keen interest in the sciences, literature, and philosophy. John recognized early on that his son was no ordinary child, and he provided an environment that encouraged exploration, experimentation, and intellectual freedom. Maxwell's mother, Frances Kay, brought a gentle and nurturing influence, balancing the household with warmth, empathy, and encouragement for her son's pursuits. Growing up in this environment, Maxwell absorbed both the analytical rigor of his father and the imaginative encouragement of his mother, a combination that would prove crucial in shaping the mind of one of the greatest scientific thinkers in history. Even as a young boy, Maxwell displayed signs of extraordinary intelligence. At the age of 8, he could already solve complex arithmetic problems and showed a remarkable memory, recalling entire poems and passages of text with ease. But what truly distinguished him from other children was his relentless curiosity about the natural world. He would spend hours observing the skies, studying the behavior of animals, and examining the patterns of plants in the Scottish countryside. Nothing escaped his notice. The intricate symmetry of a snowflake, the flight of a bird, or the way sunlight reflected off the surface of water captured his attention and fueled questions about the underlying laws that governed these phenomena. His curiosity was not idle, it was analytical, inquisitive, and deeply persistent. Maxwell's early education was unconventional yet profoundly effective. He was initially taught at home by his father and local tutors, who recognized the need to nurture his unique talents rather than confine him to rigid curricula. His father encouraged him to ask questions and to seek understanding, rather than simply memorize facts. Maxwell's fascination with nature extended beyond theoretical speculation. He was drawn to experimentation. Even as a young boy, he conducted small scientific experiments using whatever materials he could find around the house. He was known to build rudimentary mechanical devices, test the properties of light and color using prisms, and even experiment with the behavior of fluids and magnets. His playtime was indistinguishable from inquiry. For Maxwell, the act of exploring the world was inseparable from the joy of learning. The Scottish landscape itself played a formative role in Maxwell's early development. Edinburgh, with its cobblestone streets, grand architecture, and proximity to the wild expanses of the Scottish countryside, offered a stimulating environment for a young mind. Summers spent in the countryside were particularly influential. He roamed hills, rivers, and woodlands, observing nature with meticulous attention. He would sketch plants, record the flight patterns of birds, and map the trajectories of falling objects. These early observations were more than just hobbies, they were the first seeds of scientific thought, teaching him how to notice patterns, hypothesize relationships, and test ideas in the real world. Maxwell's early fascination with color and light was particularly noteworthy. He was captivated by the way sunlight passed through glass, creating a spectrum of colors on walls, and he often experimented with lenses and prisms to study the behavior of light. These early experiments, carried out long before he would become a formal scientist, demonstrated both creativity and rigor. Maxwell was developing the ability to combine empirical observation with theoretical reasoning, a skill that would define his later work in electromagnetism. In his childhood sketches and notes, we see the seeds of the visual imagination that would allow him to conceptualize abstract phenomena in physics in ways that few could comprehend. Friendships and mentorship also played a significant role in nurturing Maxwell's curiosity. Although he was a solitary thinker by nature, he formed close bonds with his family and a few local friends who shared his intellectual interests. These relationships encouraged discussion, debate, and collaboration even at a young age. Through conversations with his father, tutors, and friends, Maxwell learned the value of questioning assumptions, seeking evidence, and refining ideas through dialogue. This early social environment reinforced his scientific instincts, teaching him that knowledge is not merely accumulated in isolation, but is enriched through engagement with others. Maxwell's intellectual development during these early years was also shaped by the Scottish Enlightenment's lingering influence. Edinburgh had been a center of philosophical, scientific, and mathematical thought for decades. The intellectual atmosphere of the city, with its libraries, lectures, and learned societies, exposed Maxwell to ideas that encouraged curiosity and critical thinking. Though he was only a child, he was aware of the achievements of past Scottish thinkers and absorbed the spirit of inquiry that emphasized reason, experimentation, and observation. This cultural backdrop helped foster a mindset that valued both precision and creativity, qualities that became hallmarks of his scientific work. One of the most striking features of Maxwell's early development was his ability to connect seemingly unrelated phenomena. For instance, he noticed patterns in nature that linked color, light, and motion, or symmetry in plants that mirrored mathematical principles. This ability to see hidden connections would later become a cornerstone of his scientific achievements, allowing him to unify electricity, magnetism, and light in ways that no one before him had envisioned. Maxwell was not content with surface-level understanding. He sought the underlying order of the universe, the laws that governed both the smallest and largest scales of reality. Despite his prodigious abilities, Maxwell's childhood was not without challenges. He suffered from periods of illness and frailty, which sometimes interrupted his studies and experiments. Yet even during these times, his mind remained active. Confined to bed, he would read voraciously, solve mental puzzles, and contemplate scientific questions. These moments of quiet reflection reinforced the importance of imagination and thought experiments in his intellectual toolkit. Maxwell learned early on that rigorous thinking did not always require a laboratory or instruments. Careful observation, logical reasoning, and creative insight could yield profound understanding. The family environment, too, played a role in shaping his approach to science. Maxwell's parents encouraged him to pursue knowledge for its own sake, rather than for fame or recognition. This principle instilled a deep sense of intellectual integrity and curiosity. Maxwell did not seek to impress others, he sought to uncover truth and understand the universe. This motivation would later drive him to tackle some of the most challenging problems in physics, not for accolades, but because he was genuinely fascinated by the mysteries of nature. Maxwell's early fascination with geometry and mathematics was another critical aspect of his development. He delighted in solving complex problems, visualizing shapes, and exploring the relationships between numbers and space. These mathematical skills were not purely abstract, he used them as tools to model the physical world. By combining observation with mathematics, Maxwell was developing a framework for understanding phenomena that went far beyond descriptive science. His early exposure to mathematical reasoning laid the groundwork for his later ability to express physical laws with elegance, clarity, and precision. Even in childhood, Maxwell exhibited a rare balance of imagination and discipline. While he was curious and playful, experimenting with colors, mechanical devices, and natural phenomena, he also approached problems systematically. He recorded observations meticulously, sought patterns, and tested ideas repeatedly. This balance allowed him to explore boldly without losing rigor, a quality that distinguished him from other young prodigies. Maxwell's early habits, curiosity guided by careful observation and disciplined reasoning, became the foundation upon which his later scientific breakthroughs would rest. Maxwell's early years were also marked by an intuitive sense of scientific wonder. He did not merely learn facts, he absorbed the beauty and mystery of the world around him. From the intricate patterns in nature to the behavior of light and color, he developed a deep appreciation for the elegance of physical laws. This aesthetic sensibility informed his later work, where the elegance of equations and the symmetry of physical laws were as important to him as their predictive power. Maxwell understood that science was not just a technical pursuit, but a way of seeing the world in its full complexity and harmony. By the time Maxwell reached adolescence, his reputation as an extraordinary intellect was already evident. Tutors and family friends recognized that he possessed a rare combination of insight, creativity, and analytical skill. His early experiments, sketches, and observations foreshadowed the groundbreaking contributions he would make to physics. The Scottish landscape, the intellectual atmosphere of Edinburgh, and the nurturing environment of his family all converged to cultivate a mind capable of profound insight. Maxwell's early years were a testament to the power of curiosity, observation, and thoughtful reflection in shaping scientific genius. Through his childhood and early adolescence, Maxwell embodied a unique synthesis of traits: a love of nature, a fascination with mathematics, a talent for observation, a disciplined approach to inquiry, and a playful imagination. These qualities, nurtured in the Scottish environment and his supportive family, formed the bedrock of his later scientific achievements. Maxwell's early curiosity was not a fleeting interest. It was a persistent, guiding force that shaped his approach to the world, prepared him to challenge conventional thinking, and ultimately enabled him to lay the foundations for modern physics. In reflecting on Maxwell's formative years, it becomes clear that his genius was not sudden or accidental. It was the product of a rich interplay between innate talent, a stimulating environment, intellectual mentorship, and a deep, abiding curiosity about the world. From his earliest experiments with light and color to his meticulous observations of nature, Maxwell demonstrated a pattern of inquiry that would define his life's work. The Scottish boy who roamed the hills and rivers of Edinburgh, notebook in hand, was already thinking in ways that would transform human understanding of the universe. His early years remind us that curiosity, when nurtured and guided by observation and reason, can yield insights that change the world. As Maxwell moved into his teenage years, the intensity of his curiosity only deepened. The Scottish countryside remained his laboratory, and the pages of his notebooks became repositories for meticulous observations, speculative sketches, and imaginative theories. His excursions through the hills and rivers were not merely recreational, they were structured experiments in observation and analysis. Maxwell began to ask questions that reached beyond the visible and immediate, pondering the forces behind natural phenomena. He experimented with reflections and refractions of light, noting angles, measuring colors, and considering the behavior of shadows. These experiments, simple though they may have seemed, laid the groundwork for his later groundbreaking work on electromagnetic theory, where light itself would be revealed as a wave phenomenon. By the age of 12, Maxwell had already begun to demonstrate a capacity for abstract thinking that set him apart from his peers. While other children focused on rote learning and the repetition of facts, Maxwell engaged with ideas conceptually. He would contemplate the behavior of planets, the flow of water, and the patterns of weather, seeking the principles that connected these diverse observations. His notebooks from this period show a mind at work, grappling with mathematical relationships and visual patterns, exploring hypothetical mechanisms, and speculating about the unseen forces that governed the natural world. It was a mind in constant motion, moving seamlessly between observation, analysis, and imagination. Maxwell's intellectual environment continued to play a critical role in shaping his development. Tutors recognized the need to challenge him beyond standard curricula, providing him with complex mathematical problems and advanced readings in science. They encouraged independent study, allowing him the freedom to explore subjects that captured his attention. Maxwell was voracious in his appetite for knowledge. He read widely in mathematics, physics, and natural philosophy, often drawing connections across disciplines in ways that surprised even his mentors. His exposure to the works of Isaac Newton, Michael Faraday, and other great scientists of the era fueled his ambition and imagination, inspiring him to think about questions that had not yet been fully addressed by anyone. During these formative years, Maxwell also began to develop a sophisticated understanding of experimentation. He realized that careful measurement, repeated testing, and critical reflection were essential to understanding natural laws. Simple play with magnets, light prisms, and mechanical devices evolved into more structured experimentation. He designed experiments with clear objectives, controlled variables, and meticulous recording of results. He even began to formulate early hypotheses about the relationships between forces, energy, and matter. These practices, learned and refined during adolescence, would become the methodological foundation for his later work in electromagnetism and wave theory. Maxwell's early fascination with light and color continued to expand. He began to explore the nature of color mixing and perception, conducting experiments with overlapping colored filters and prisms. He observed how colors blended and changed depending on angles and distances, noting patterns with a precision that foreshadowed his later contributions to the understanding of electromagnetic waves. His work in color theory was not only experimental but also mathematical. He sought to quantify his observations, developing early formulations to predict how colors would interact. This blending of observation, experimentation, and mathematical reasoning was a hallmark of Maxwell's approach and demonstrated an extraordinary maturity for someone still in his teenage years. Friendships and mentorship during this period remained critical. Maxwell formed close bonds with peers who shared intellectual interests, creating informal circles of discussion and debate. Conversations with mentors and tutors encouraged critical thinking and reinforced the value of questioning assumptions. Maxwell learned to defend his ideas, to revise them in the face of evidence, and to seek deeper understanding rather than superficial explanations. This intellectual engagement cultivated resilience and adaptability, qualities essential for a life devoted to scientific discovery. Around the age of 14, Maxwell began to gain recognition for his talents beyond the confines of his family and immediate tutors. He entered local scientific competitions, submitted essays, and participated in exhibitions of experimental work. His submissions demonstrated originality, rigor, and creativity, earning him admiration and attention from established scientists and educators. This early recognition reinforced his dedication and confidence, showing him that his unique approach to observation and analysis had value in the wider scientific community. Maxwell's formal education was beginning to take shape alongside his independent studies. Though initially educated at home, he later attended the Edinburgh Academy, a school known for its strong emphasis on classical education, mathematics, and science. Here, Maxwell encountered more structured instruction, which both challenged and complemented his independent explorations. The academy exposed him to a broader intellectual environment, introducing him to peers with varying levels of aptitude and interest. This diversity allowed Maxwell to develop not only technical skills, but also the social and communicative abilities necessary for a scientist who would later collaborate widely with colleagues. At the Edinburgh Academy, Maxwell's aptitude for mathematics became increasingly evident. He tackled complex problems with facility, often surpassing the expectations of his instructors. His notebooks from this period reveal a remarkable clarity of thought and a willingness to engage with abstract concepts. Geometry, algebra, and early calculus exercises were not mere assignments, they were opportunities for experimentation, problem solving, and the development of logical structures. Maxwell's ability to connect mathematical formalism with physical intuition was already emerging, foreshadowing the elegance and power of his later theoretical work. Maxwell's curiosity about the physical world was not confined to the classroom. He continued to conduct experiments and observations outside of school, often devising instruments and apparatus to test his ideas. Simple mechanical models of planetary motion, rudimentary optical devices, and small electrical circuits were all part of his exploratory work. Each experiment was recorded with meticulous detail, reflecting his growing understanding of scientific methodology and his commitment to systematic inquiry. Through these experiences, Maxwell learned the importance of precision, reproducibility, and critical evaluation, lessons that would become central to his later achievements in physics. His engagement with contemporary scientific literature also deepened during his teenage years. Maxwell read extensively, not only in mathematics and physics but also in natural philosophy, astronomy, and chemistry. He absorbed the experimental findings and theoretical insights of leading scientists, reflecting on them critically and attempting to synthesize new ideas. This process of reading, questioning, and integrating knowledge strengthened his capacity for independent thought and laid the groundwork for the revolutionary synthesis he would achieve in electromagnetism. Maxwell's notebooks from this period contain a mix of direct observation, theoretical speculation, and practical experimentation, demonstrating the seamless integration of empirical and conceptual thinking that would characterize his mature work. Maxwell's teenage years were also marked by the cultivation of patience and perseverance. Experiments often failed, observations were sometimes inconclusive, and mathematical challenges were daunting. Yet Maxwell approached these setbacks not as obstacles but as opportunities for deeper understanding. He developed resilience, learning to analyze errors, refine techniques, and persist in the face of difficulty. This capacity for disciplined inquiry and reflection would serve him throughout his scientific career, enabling him to tackle problems that had resisted solution for decades. Another defining aspect of Maxwell's early development was his imaginative capacity. While he was grounded in observation and experimentation, he also possessed the ability to envision phenomena that could not be directly observed. This imagination allowed him to conceptualize abstract entities, visualize electromagnetic fields, and anticipate relationships between forces. His early notebooks reveal sketches and diagrams that suggest a mind capable of mental modeling, imagining complex interactions, and predicting outcomes based on logical reasoning. This combination of imagination and rigor would later allow him to unify electricity, magnetism, and light into a coherent theoretical framework. Maxwell's parents continued to play a crucial role during these years. They encouraged him to pursue knowledge for its own sake, emphasizing the intrinsic value of understanding the natural world. This ethos of curiosity, rather than ambition for recognition, shaped Maxwell's approach to science. He learned that discovery was not a means to fame, but a way of engaging with the universe, seeking truth, and contributing to collective understanding. This perspective nurtured intellectual humility, ethical responsibility, and a focus on enduring questions rather than transient achievements. By the time he reached the age of 16, Maxwell had developed an extraordinary combination of skills: acute observational ability, analytical rigor, imaginative capacity, and disciplined experimentation. He had absorbed foundational knowledge in mathematics, physics, and natural philosophy, while simultaneously cultivating habits of independent inquiry, critical thinking, and meticulous record-keeping. These attributes provided a robust intellectual framework upon which his later theoretical breakthroughs would be built. The young Scottish boy, roaming hills with a notebook in hand, was now prepared to enter higher education and confront the most profound scientific questions of his time. Maxwell's teenage years also set the stage for the first formal acknowledgement of his genius in the scientific community. Teachers, mentors, and local intellectual circles recognized his extraordinary talent, providing encouragement and opportunities for more advanced study. This external validation reinforced his internal drive, instilling confidence while also exposing him to the broader intellectual currents of the era. He was increasingly aware that the natural world could be understood systematically, that patterns and laws governed its behavior, and that he possessed the capacity to uncover these principles through careful thought and experimentation. In reflecting on this stage of Maxwell's life, it becomes clear that his early curiosity, nurtured by family, tutors, and the Scottish environment, was far from idle. It was disciplined, methodical, and imaginative, preparing him for the profound theoretical work that would later transform physics. Maxwell's early years demonstrate that genius is rarely sudden or isolated. It is the result of persistent curiosity, careful observation, disciplined practice, and a supportive intellectual environment. By cultivating these qualities from a young age, Maxwell became equipped not merely to observe the natural world, but to understand it at a fundamental level, laying the foundation for a life of transformative scientific discovery. Through adolescence, Maxwell exemplified the integration of imagination and reason, curiosity and discipline, observation and abstraction. His formative experiences, roaming the hills of Scotland, conducting experiments with light, color, and mechanics, engaging with mentors, and studying mathematics rigorously, all contributed to the intellectual architecture that would enable him to later unify electricity, magnetism, and light. Maxwell's early years remind us that the seeds of revolutionary ideas often take root in quiet observation, nurtured curiosity, and patient reflection long before the world takes notice of their full significance. By the time Maxwell approached adulthood, he was not only intellectually prepared for formal higher education, but already thinking in ways that would challenge established scientific paradigms. The foundations of modern physics were being laid in the notebooks of a Scottish teenager who asked questions that no one else had thought to ask and who combined play, experimentation, and disciplined study in ways that would forever change our understanding of the universe. Maxwell's early life illustrates that genius emerges not only from innate talent, but from the persistent, guided pursuit of understanding. A pursuit that begins in curiosity and observation, flourishes in disciplined study, and matures in imaginative insight. As James Clerk Maxwell transitioned from his formative childhood into adolescence, his academic journey became increasingly structured and formalized, allowing his prodigious talents to flourish within institutional settings. The foundations laid in his early years of curiosity, observation, and experimentation were now complemented by rigorous instruction in mathematics, natural philosophy, and the classical sciences. His formal education, first at the University of Edinburgh and later at Cambridge, was pivotal in shaping the intellectual frameworks that would allow him to make revolutionary contributions to physics. These years were not merely a period of rote learning, they were a time of synthesis, exploration, and profound intellectual growth, in which Maxwell learned to bridge the gap between empirical observation and abstract reasoning. At the University of Edinburgh, Maxwell was immersed in a stimulating intellectual environment, one that encouraged both inquiry and critical thinking. Edinburgh at the time was a vibrant center of learning, with a rich tradition in science, mathematics, and philosophy. The city had produced some of the most influential thinkers of the Scottish Enlightenment, and although Maxwell arrived decades later, the legacy of intellectual rigor and curiosity was deeply ingrained in the academic culture. Within this context, Maxwell was exposed to lectures, laboratories, and discussions that introduced him to the broader questions of physics, mathematics, and natural philosophy. He quickly demonstrated a remarkable capacity for mastering complex concepts, moving beyond the curriculum with ease and seeking out additional material to satisfy his insatiable curiosity. Maxwell's time at Edinburgh provided him with a foundation in classical mathematics and physics. He was trained in geometry, algebra, and the early elements of calculus, mastering techniques that would later enable him to formulate his groundbreaking equations. Beyond technical proficiency, Maxwell's education emphasized logical reasoning, careful deduction, and the importance of rigor in argumentation. Professors recognized his extraordinary abilities, often providing him with challenges beyond the standard curriculum. In response, Maxwell displayed both intellectual agility and perseverance, mastering material that challenged even older students. His capacity to synthesize information from multiple disciplines became increasingly evident, as he could connect mathematical abstractions with physical phenomena in ways few of his peers could. During his Edinburgh years, Maxwell was particularly influenced by the work of contemporary scientists and mathematicians. He studied the experimental findings of Michael Faraday, whose explorations in electricity and magnetism would later provide the empirical foundation for Maxwell's theoretical unification of these forces. Faraday's approach, emphasizing careful observation, experimentation, and visualization of field lines, left a lasting impression on Maxwell. Although Faraday lacked formal mathematical training, Maxwell combined Faraday's intuitive experimental insights with the powerful tools of mathematics, a synthesis that became a defining feature of his later work. The exposure to Faraday's ideas during his Edinburgh education inspired Maxwell to consider the hidden structures underlying physical phenomena and to think about the ways in which seemingly disparate forces might be unified within a coherent theoretical framework. Maxwell's fascination with light and color, evident in his childhood, was nurtured further during his Edinburgh education. He explored the principles of optics, studying the behavior of lenses, prisms, and the properties of reflection and refraction. These studies were not merely theoretical. He continued to conduct hands-on experiments, investigating the ways in which light interacted with materials, the dispersion of colors, and the phenomena of interference and polarization. The combination of rigorous instruction and independent experimentation allowed Maxwell to develop a sophisticated understanding of the behavior of light, knowledge that would later contribute to his discovery that light itself is an electromagnetic wave. A particularly formative aspect of Maxwell's Edinburgh years was his engagement with mathematics as a language for understanding the physical world. He was introduced to advanced calculus, differential equations, and the mathematical treatment of forces and motion. Unlike many students who approached mathematics as a purely abstract exercise, Maxwell learned to use it as a tool for modeling and predicting natural phenomena. He developed an appreciation for the elegance and power of mathematical formalism, recognizing that the laws of nature could be expressed concisely and universally through equations. This understanding of mathematics as both a descriptive and predictive instrument became central to his later work in electromagnetism and kinetic theory. Beyond academics, Maxwell's time at Edinburgh was marked by intellectual exploration and experimentation. He frequently spent hours in laboratories, observing experiments and designing his own. He built mechanical models, optical instruments, and early electrical apparatuses, using them to test hypotheses and explore phenomena. These experiments, while modest in scale, demonstrated a methodological sophistication unusual for someone of his age. He combined careful measurement, repeated observation, and critical evaluation, developing habits of inquiry that would become second nature in his professional career. Maxwell's education was thus not confined to lecture halls and textbooks. It was lived, embodied in the act of exploration and in the ongoing dialogue between theory and experiment. During this period, Maxwell also cultivated a network of mentors and intellectual peers who played a critical role in his development. Professors, tutors, and older students recognized his talent and provided guidance, challenging him with complex problems and encouraging independent thinking. These relationships were not merely hierarchical. They fostered dialogue, debate, and critical reflection. Maxwell learned the value of questioning assumptions, testing ideas rigorously, and engaging with alternative viewpoints. This collaborative dimension of his education helped him develop the intellectual flexibility and confidence necessary to tackle the unprecedented problems he would later address in physics. As Maxwell matured intellectually at Edinburgh, he began to grapple with questions that went beyond the standard curriculum. He was deeply interested in the nature of forces, the behavior of matter, and the principles governing motion and energy. He questioned the mechanisms underlying electricity and magnetism, explored the propagation of light, and contemplated the possibility of underlying unity among physical phenomena. These questions were not idle speculation. Maxwell sought answers through careful study, mathematical analysis, and experimental investigation. The education he received provided him not only with the tools to ask these questions, but also with the intellectual discipline to pursue answers rigorously. Upon completing his studies at Edinburgh, Maxwell proceeded to Cambridge University, where he entered Trinity College in 1850. Cambridge represented both a continuation and an intensification of his educational trajectory. The intellectual environment was rich with tradition, rigor, and competition, providing a stage on which Maxwell's abilities could be fully tested and refined. At Cambridge, he encountered a curriculum that emphasized mathematics as the foundation of scientific understanding, particularly through the mathematical tripos, a notoriously demanding series of examinations designed to challenge the intellects of the brightest students in Britain. Maxwell thrived in this environment, demonstrating mastery over the most advanced topics in mathematics, including calculus, algebra, geometry, and mathematical physics. At Cambridge, Maxwell's engagement with mathematics became increasingly sophisticated. He was encouraged to explore the frontiers of the discipline, tackling problems that required not only technical skill, but creativity and insight. He became particularly interested in analytical methods, the study of dynamics, and the mathematical representation of physical phenomena. Here, Maxwell began to integrate the experimental and observational knowledge he had gained in Edinburgh with formal mathematical techniques, developing the capacity to model complex physical systems. This synthesis of empirical and theoretical thinking became the hallmark of his approach to science. Maxwell's time at Cambridge was also marked by exposure to the broader intellectual currents of the period. He read widely in mathematics, physics, astronomy, and natural philosophy, engaging with the ideas of past and contemporary thinkers. The works of Newton, Laplace, and Faraday were particularly influential. Newton's laws provided the foundation for mechanics. Laplace's celestial mechanics demonstrated the power of mathematical modeling, and Faraday's experimental insights inspired Maxwell to seek unifying principles in electricity and magnetism. Cambridge provided the structure, discipline, and intellectual stimulation necessary for Maxwell to synthesize these diverse influences into a coherent vision of physical reality. Experimentation and observation continued to play a critical role in Maxwell's Cambridge education. Though the university emphasized mathematical rigor, Maxwell complemented formal instruction with practical investigation. He constructed instruments, conducted experiments, and tested theoretical ideas against empirical evidence. This hands-on approach allowed him to maintain a strong connection between abstract mathematics and the physical world, ensuring that his theoretical models remained grounded in observable reality. Maxwell's ability to move seamlessly between theory and experiment distinguished him from many of his contemporaries, who were often confined to either pure mathematics or pure empirical work. Maxwell's achievements at Cambridge were formally recognized when he excelled in the mathematical tripos, achieving distinction as a top performer. This accomplishment brought him into the intellectual spotlight and provided access to a network of scholars and resources that furthered his development. However, Maxwell's success was not measured solely in accolades. It was reflected in his growing ability to think independently, to formulate novel hypotheses, and to approach problems with both creativity and precision. His Cambridge education had provided not only knowledge, but the methodological and conceptual tools necessary for scientific innovation. During this period, Maxwell's engagement with Faraday's work deepened. He sought to translate Faraday's qualitative, experimental insights into quantitative, mathematical form. Faraday's field lines, once visual and intuitive, became mathematical constructs in Maxwell's mind. This intellectual endeavor, bridging the gap between intuitive experimentation and abstract formalism, was facilitated by the rigorous mathematical training he received at Cambridge. Maxwell's education had equipped him with the ability to see underlying structures, to formulate general laws, and to express them through elegant and predictive equations. By the time Maxwell completed his formal education at Cambridge, he had transformed from a curious Scottish child into a fully formed intellectual capable of addressing some of the most profound questions in physics. His education had not merely imparted knowledge, it had cultivated habits of rigorous observation, disciplined reasoning, creative synthesis, and critical engagement. Edinburgh had provided the foundation, Cambridge had refined and expanded it, and the combination prepared Maxwell to enter the scientific world as a thinker poised to revolutionize our understanding of the universe. Maxwell's years at Edinburgh and Cambridge illustrate that education is not merely the transmission of facts, but the cultivation of a mind capable of inquiry, synthesis, and innovation. He exemplified the integration of curiosity, imagination, observation, and analytical rigor. These formative educational experiences laid the groundwork for his later achievements, including the unification of electricity and magnetism, the mathematical modeling of electromagnetic waves, and the conceptualization of light as an electromagnetic phenomenon. In every sense, Maxwell's formal education enabled him to transform the questions of his youth into the groundbreaking answers of his scientific career. As Maxwell progressed through his studies at Cambridge, his intellectual development accelerated in ways that would prepare him for some of the most profound contributions to physics ever made. Cambridge was not only a center of academic excellence, it was also a crucible of intellectual challenge, where the brightest minds of Britain were tested rigorously in mathematics, physics, and natural philosophy. The demanding environment of the mathematical tripos examinations pushed Maxwell to refine his analytical skills, develop creative problem-solving abilities, and cultivate the intellectual resilience necessary to tackle questions that had eluded even the most experienced scientists. In this environment, he honed not only his knowledge, but the very habits of thought that would allow him to innovate in physics. During his years at Trinity College, Maxwell immersed himself in the study of mathematical physics, a field that combined abstract mathematical reasoning with the empirical study of physical phenomena. He excelled in mechanics, celestial dynamics, and the mathematical treatment of forces, demonstrating both exceptional technical ability and a profound conceptual understanding. His notebooks reveal a mind constantly at work, exploring problems independently, testing assumptions, and seeking general principles that could unify disparate observations. Unlike many students who approached mathematics as an abstract exercise, Maxwell consistently sought to apply his knowledge to the natural world, using equations to describe and predict physical behavior. A central focus of Maxwell's Cambridge education was the study of dynamics, the mathematical framework for understanding motion and forces. He engaged deeply with Newtonian mechanics, exploring the laws of motion and gravitation with both rigor and creativity. He extended these principles, contemplating the interactions of multiple bodies, the behavior of fluids, and the propagation of waves. These studies required not only technical mastery, but also the capacity to visualize complex systems, to anticipate outcomes, and to understand the underlying structures that govern their behavior. Maxwell's work in dynamics laid the foundation for his later contributions to electromagnetic theory, as it cultivated the ability to think in terms of forces, fields, and interactions at a fundamental level. Cambridge also offered Maxwell the opportunity to engage with cutting-edge developments in experimental science. Although the university emphasized theoretical rigor, Maxwell supplemented his studies with practical investigation. He spent long hours in laboratories, constructing devices, performing measurements, and observing phenomena firsthand. These experiences reinforced the connection between theory and experiment, ensuring that his abstract mathematical models remained grounded in observable reality. Maxwell's capacity to bridge these realms, to translate experimental observation into precise mathematical language, was emerging as a defining characteristic of his scientific approach. Maxwell's interaction with his professors and peers at Cambridge played a crucial role in shaping his intellectual development. He sought guidance from mentors who recognized his talent, engaging in discussions that challenged him to refine his reasoning and articulate his ideas clearly. These conversations often extended beyond the classroom, involving detailed analysis of contemporary scientific problems, critical evaluation of experimental methods, and exploration of theoretical possibilities. The mentorship and dialogue Maxwell experienced at Cambridge provided both intellectual stimulation and the support necessary for him to explore innovative approaches to physics. During this period, Maxwell's engagement with the work of Michael Faraday deepened significantly. Faraday's experimental insights into electricity, magnetism, and the nature of fields fascinated Maxwell, who sought to translate these qualitative observations into mathematical form. Faraday had conceived of lines of force and the idea of fields permeating space, but he lacked the mathematical tools to formalize these concepts. Maxwell's rigorous training at Cambridge enabled him to bridge this gap, developing the mathematical framework that would become his famous equations. The Cambridge education, with its emphasis on analytical reasoning, rigorous proof and synthesis of complex ideas, was essential in equipping Maxwell to accomplish this intellectual feat. In addition to his formal studies, Maxwell undertook independent research projects that reflected his growing intellectual maturity. He explored problems in optics, studying the behavior of light, color, and polarization. He investigated the kinetic theory of gases, applying mathematical analysis to understand molecular motion and thermodynamic properties. These endeavors required a delicate balance of creativity, precision, and perseverance, and they demonstrated Maxwell's ability to pursue complex questions with both depth and originality. His early experiments, though modest in scale, were exercises in methodical investigation, reinforcing his habits of observation, measurement, and critical evaluation. Maxwell's work at Cambridge also included contributions to geometry and algebra, disciplines that would provide the mathematical tools necessary for his later theoretical breakthroughs. He studied the properties of curves, surfaces, and higher dimensional spaces, exploring how mathematical structures could model physical phenomena. These studies cultivated both precision and imagination, training him to visualize abstract relationships and to represent them in mathematical terms. The combination of geometric insight and algebraic technique was crucial for his later work in electromagnetic theory, where spatial relationships and field interactions required both conceptual and formal sophistication. Social and intellectual interactions at Cambridge further enriched Maxwell's education. He engaged with peers who shared his interests, forming informal study groups, exchanging ideas, and debating complex problems. These interactions encouraged intellectual flexibility and reinforced the value of collaboration in scientific inquiry. Maxwell also participated in academic societies and lectures, exposing him to broader currents of thought and emerging discoveries. The combination of formal instruction, independent study, and social engagement created a dynamic environment in which Maxwell's intellect could thrive, encouraging both depth of understanding and originality of thought. A particularly formative aspect of Maxwell's Cambridge experience was his work on the mathematical analysis of Faraday's experimental findings. Faraday had observed that electric and magnetic effects seemed to propagate through space and that they were interconnected, but he had not expressed these ideas in precise mathematical form. Maxwell applied his mathematical training to formalize these observations, introducing equations that described how electric and magnetic fields interact, vary over time, and propagate as waves. This synthesis of mathematics and experimentation, made possible by the rigorous foundation laid at Cambridge, became the cornerstone of his later revolutionary work in electromagnetic theory. Maxwell's time at Cambridge also reinforced the importance of intellectual rigor and precision. The mathematical tripos required not only mastery of content, but also the ability to solve novel and challenging problems under pressure. Maxwell's success in this demanding environment reflected both his technical skill and his disciplined approach to problem solving. He learned to approach complex questions systematically, to verify assumptions, and to ensure that conclusions were supported by evidence and logic. These habits of disciplined inquiry became fundamental to his later scientific methodology, underpinning the formulation of theories that would withstand scrutiny for generations. Beyond his studies in mathematics and physics, Maxwell cultivated a broad intellectual perspective at Cambridge. He read extensively in philosophy, natural history, and literature, developing a capacity for interdisciplinary thinking that informed his scientific approach. He considered not only the technical details of phenomena, but also the conceptual and philosophical implications of his work. This breadth of intellectual engagement allowed Maxwell to see connections between seemingly disparate domains, an ability that would prove essential in unifying electricity, magnetism, and light. His Cambridge education nurtured both depth and breadth, combining specialized expertise with a holistic understanding of science and knowledge. Maxwell's education at Cambridge also strengthened his capacity for imaginative thinking, a trait that would prove crucial in his later theoretical innovations. He was encouraged to think beyond established paradigms, to explore hypothetical scenarios, and to conceptualize phenomena that could not be directly observed. This imaginative dimension, nurtured alongside rigorous analytical training, enabled Maxwell to visualize electromagnetic fields, model interactions mathematically, and anticipate the propagation of electromagnetic waves. His Cambridge years taught him that true scientific insight requires not only technical mastery, but also creativity and the ability to envision possibilities beyond the immediately observable. By the end of his formal education at Cambridge, Maxwell had achieved mastery over the mathematical and conceptual tools necessary to engage with the most challenging questions in physics. He had absorbed the lessons of observation, experimentation, and critical reasoning from his Edinburgh studies, refined them through rigorous mathematical training, and expanded them through exposure to contemporary scientific literature and mentorship. This combination of preparation and opportunity equipped Maxwell to begin the work that would transform the understanding of electricity, magnetism, and light, placing him at the forefront of scientific innovation. Maxwell's education was more than the accumulation of knowledge, it was the cultivation of intellectual habits that enabled discovery. Observation, imagination, mathematical reasoning, disciplined inquiry, and the integration of theory and experiment were all fostered during his years at Edinburgh and Cambridge. The interplay of formal instruction, independent research, mentorship, and social engagement created an environment in which Maxwell's natural curiosity could mature into a structured, disciplined, and innovative scientific intellect. These years were formative not only in terms of content learned, but in the development of a mindset capable of revolutionary thought. Through his formal education, Maxwell was able to combine empirical observation with abstract reasoning, experiment with mathematical models, and engage critically with contemporary scientific thought. He learned to articulate ideas clearly, test hypotheses rigorously, and seek general principles that could unify diverse phenomena. This education laid the groundwork for his later achievements, including the formulation of Maxwell's equations, the unification of electricity and magnetism, and the demonstration that light is an electromagnetic wave. Without the intellectual and methodological foundation provided by his education at Edinburgh and Cambridge, Maxwell's later contributions might never have been possible. Maxwell's years of formal study also illustrate the transformative power of a well-rounded education. Exposure to rigorous mathematics, empirical science, mentorship, and intellectual discourse cultivated a mind capable of both precision and creativity, of observation and imagination, of technical mastery and conceptual synthesis. Maxwell emerged from this period not merely as a student with knowledge, but as a thinker equipped to reshape the very foundations of physics, to bridge experiment and theory, and to explore questions that would define modern science. As Maxwell left Cambridge to begin his professional career, he carried with him not only a profound knowledge of mathematics and physics, but also a set of intellectual habits, conceptual frameworks, and imaginative capabilities that would allow him to make revolutionary contributions. The education he received was not simply an academic achievement. It was the crucible in which the mind of one of history's greatest scientists was forged. The lessons of observation, disciplined reasoning, mathematical rigor, and creative synthesis acquired at Edinburgh and Cambridge became the foundation upon which the edifice of modern physics would be built. James Clerk Maxwell's journey from a prodigious student to a scientific revolutionary reached its defining stage in his exploration of electricity and magnetism. While electricity and magnetism had been studied for decades, their relationship remained mysterious and fragmented. Observations of electric currents, magnetic effects, and the behavior of charges had been cataloged by scientists such as Michael Faraday and André Marie Ampère, but no unified theoretical framework existed. Maxwell approached this challenge with a unique combination of mathematical rigor, physical intuition, and imaginative insight, shaped by his rigorous education and early experiments. He sought not merely to describe individual phenomena, but to uncover the underlying laws that governed all electric and magnetic effects. Maxwell's work began with careful consideration of Faraday's experimental discoveries. Faraday had observed that electric currents produced magnetic effects, and that changing magnetic fields could induce electric currents. He had conceived of lines of force, visualizing fields as dynamic structures extending through space. Faraday's approach, deeply intuitive and visual, lacked the formal mathematical representation that could generalize and predict the behavior of these forces. Maxwell recognized the power and significance of Faraday's insights, but he also saw their limitations. Where Faraday had offered qualitative descriptions, Maxwell envisioned quantitative relationships expressed through precise mathematical equations. This ability to translate empirical observations into a coherent theoretical framework became the hallmark of his approach. At the core of Maxwell's endeavor was the belief that electric and magnetic phenomena were not separate, isolated effects but manifestations of a single underlying reality. This insight required a radical shift in thinking, moving beyond the traditional view of forces acting instantaneously across space to a vision of fields permeating the universe. Maxwell imagined space itself as filled with invisible lines of force, transmitting interactions between charges and magnets. This conceptual leap allowed him to unify previously disconnected phenomena and to predict behaviors that had not yet been observed. The idea of a field as a real, dynamic entity was revolutionary, challenging prevailing mechanistic views and setting the stage for the modern understanding of physics. To formalize these ideas, Maxwell drew upon his extensive mathematical training. He applied techniques from calculus, differential equations, and vector analysis to describe the behavior of electric and magnetic fields. His goal was to express Faraday's qualitative insights in precise, predictive form. By doing so, Maxwell created a set of equations that captured the essence of electromagnetism, how electric charges produce fields, how magnetic fields arise from currents and changing electric fields, and how these fields interact to produce observable effects. These equations, now known as Maxwell's equations, synthesized centuries of experimental knowledge into a compact, coherent, and elegant mathematical framework. The formulation of Maxwell's equations was not a simple or immediate task. It required years of study, reflection, and iterative refinement. Maxwell meticulously analyzed experimental data, scrutinized the work of predecessors, and tested his own theoretical constructs against known phenomena. He explored the implications of his equations for the propagation of electric and magnetic effects, predicting the behavior of fields in space and time. His approach combined analytical precision with imaginative modeling, allowing him to conceptualize invisible processes while ensuring that his mathematics remained grounded in observable reality. The resulting framework was both powerful and predictive, capable of explaining known phenomena and forecasting new effects yet to be measured. One of the most profound insights emerging from Maxwell's work was the realization that electric and magnetic fields could propagate as waves through space. By manipulating his equations, Maxwell demonstrated that disturbances in these fields would travel at a finite speed, which, remarkably, corresponded to the measured speed of light. This connection revealed that light itself is an electromagnetic wave, unifying the study of optics with the behavior of electric and magnetic forces. This discovery not only provided a theoretical foundation for the understanding of light, but also expanded the scope of physics, showing that electromagnetic phenomena and optical phenomena were manifestations of the same underlying principles. Maxwell's equations thus bridged previously separate domains of science, demonstrating the power of unifying theory. Maxwell's unification of electricity and magnetism also had profound implications for the concept of action at a distance. Before Maxwell, forces such as gravity, electricity, and magnetism were often conceived as instantaneous effects transmitted across space. Maxwell's field theory suggested instead that interactions occur through fields that propagate through space at a finite speed, fundamentally changing the conceptual framework of physics. This shift influenced subsequent developments, including Einstein's theory of relativity, which relied on the constancy of the speed of light and the finite propagation of interactions. Maxwell's work thus not only explained existing phenomena, but also laid the conceptual groundwork for a new understanding of space, time, and causality. The development of Maxwell's equations also exemplified his unique combination of creativity and rigor. While many of his contemporaries were skilled either in mathematics or in experimental physics, Maxwell combined both. He was able to translate Faraday's experimental intuition into precise mathematical language, retaining the physical meaning and predictive power of the original observations. His approach demonstrated the importance of integrating empirical data with abstract reasoning, showing that theoretical insight need not be divorced from experimental evidence. Maxwell's ability to navigate between these domains allowed him to achieve a level of synthesis that few others could attain. Maxwell's work did not emerge in isolation, it was the culmination of centuries of scientific inquiry. He built upon the discoveries of Coulomb, Ampere, Faraday, and others, critically analyzing their findings, reconciling apparent contradictions, and generalizing principles to create a unified framework. He extended the understanding of electrical circuits, explored the behavior of magnetic materials, and formulated the laws governing the dynamics of charges in motion. By integrating these diverse strands into a coherent whole, Maxwell demonstrated the power of synthesis in scientific discovery, showing how disparate observations could be explained through fundamental laws. The mathematical elegance of Maxwell's equations also reflected his aesthetic sensibility. He was deeply attuned to symmetry, simplicity, and conceptual clarity, seeking formulations that not only explained phenomena but did so with beauty and coherence. His equations captured the interplay of electric and magnetic fields in a compact and precise manner, reflecting both the logical structure of nature and the intellectual satisfaction of a unified theory. This aesthetic dimension was not superficial, it was integral to his approach, guiding the search for principles that were both correct and elegant, and reinforcing the idea that the laws of nature possess inherent simplicity and harmony. The publication of Maxwell's work marked a turning point in physics. While initially met with curiosity and some skepticism, his theoretical framework gradually gained recognition as its predictive power became evident. Experiments confirmed the existence of electromagnetic waves, validating Maxwell's equations and establishing the connection between electricity, magnetism, and light. Over time, his work revolutionized both theoretical and applied physics, influencing the development of radio, telecommunications, electrical engineering, and countless technologies dependent on the understanding of electromagnetic phenomena. Maxwell's equations thus had immediate scientific significance and long-term technological impact, demonstrating the transformative power of fundamental theoretical insight. Maxwell's unification of electricity and magnetism also reshaped the conceptual landscape of science. By demonstrating that light is an electromagnetic wave, he bridged the gap between the study of matter, forces, and radiation. His work suggested that the physical universe is governed by consistent, universal laws that can be described mathematically, a perspective that underpins modern physics. Maxwell's field theory provided a framework for understanding not only electromagnetism, but also the deeper relationships between energy, matter, and space, influencing the subsequent development of quantum mechanics, relativity, and modern cosmology. The process of developing Maxwell's equations illustrates the interplay of persistence, creativity, and intellectual rigor. Maxwell spent years refining his ideas, revising formulations, and testing predictions. He grappled with complex mathematical concepts, reconciled conflicting experimental results, and anticipated the implications of his theory for phenomena that had yet to be observed. His work required both disciplined attention to detail and bold conceptual leaps, a combination that allowed him to synthesize a comprehensive theory of electromagnetism. This synthesis not only explained known phenomena, but also predicted new effects, exemplifying the predictive power of a unified theoretical framework. Maxwell's approach to unifying electricity and magnetism also highlights the importance of bridging qualitative and quantitative reasoning. Faraday's qualitative insights provided the inspiration and conceptual grounding, while Maxwell's mathematical formalism transformed these ideas into a predictive, testable framework. By integrating experimental observation with rigorous analysis, Maxwell demonstrated a model of scientific inquiry in which intuition and precision reinforce each other. This approach would become a paradigm for subsequent generations of physicists, illustrating how empirical observation, mathematical reasoning, and conceptual imagination can combine to produce revolutionary insights. Maxwell's work also underscores the significance of intellectual perseverance. Many of the principles he elucidated were not immediately understood or accepted by the scientific community. The novelty of the field concept, the abstract nature of his equations, and the radical unification of phenomena challenged prevailing notions and required careful explanation and validation. Maxwell persisted, refining his formulations, clarifying their physical meaning, and demonstrating their predictive power. His patience, diligence, and commitment to understanding the natural world exemplify the qualities necessary for groundbreaking scientific achievement. Through the formulation of Maxwell's equations, James Clerk Maxwell fundamentally transformed the understanding of the physical universe. By unifying electricity and magnetism into a single coherent framework, he revealed the underlying harmony of natural forces and established the field concept as a central pillar of physics. His work provided the mathematical and conceptual foundation for modern electromagnetism, optics, and many technologies that define contemporary life. Beyond its practical significance, Maxwell's synthesis exemplified the power of human intellect to discern order, predict behavior, and uncover the hidden structures that govern the universe. Maxwell's achievement also illustrates the cumulative nature of scientific progress. He built upon centuries of experimentation, observation, and theoretical work, integrating the contributions of Faraday, Coulomb, Ampere, and others into a coherent whole. Yet he also extended these ideas in unprecedented ways, introducing concepts and equations that transformed understanding and opened new avenues of inquiry. Maxwell's work demonstrates that scientific innovation often arises from the interplay of existing knowledge, creative insight, and rigorous synthesis, a process in which the imagination of the individual interacts with the discoveries of the past to create something fundamentally new. Following the formulation of his revolutionary equations, Maxwell devoted considerable attention to exploring their implications and validating their predictions. While the equations themselves provided a mathematically coherent and elegant framework, the broader scientific community required tangible connections to observable phenomena. Maxwell understood that theory without empirical relevance risked remaining abstract speculation, so he carefully considered experimental consequences, connecting his mathematics to real-world phenomena. This approach reflected the hallmark of his scientific method, a seamless integration of theoretical insight, imaginative conceptualization, and rigorous grounding in observation. One of the most profound consequences Maxwell predicted was the existence of electromagnetic waves, disturbances in electric and magnetic fields that propagate through space. By manipulating his equations, he deduced that these waves would travel at a constant speed, which, remarkably, corresponded to the measured speed of light. This insight revealed that light itself is an electromagnetic phenomenon, fundamentally uniting the study of optics with the behavior of electric and magnetic fields. The unification of light and electromagnetism was a conceptual revolution, demonstrating that what had previously been considered distinct phenomena were in fact manifestations of the same underlying forces. Maxwell's theoretical insight transformed the understanding of light, showing that it is not merely a passive illumination of the world, but an active vibration of electric and magnetic fields propagating through space. Maxwell's prediction of electromagnetic waves opened a new realm of experimental inquiry. Although he had not directly observed these waves himself, his theoretical framework provided precise guidance for future experimentation. Physicists such as Heinrich Hertz later confirmed the existence of electromagnetic waves, validating Maxwell's predictions and demonstrating the profound predictive power of his equations. This empirical confirmation cemented Maxwell's legacy, showing that rigorous theoretical reasoning, when combined with imaginative conceptualization, could anticipate phenomena beyond the reach of contemporary observation. The eventual experimental verification of electromagnetic waves not only confirmed Maxwell's vision, but also laid the foundation for the development of modern technologies, including radio, television, radar, and wireless communications. Maxwell's work also fundamentally transformed the concept of the electromagnetic field. Prior to his synthesis, electric and magnetic effects were often conceived as occurring instantaneously between objects, with forces transmitted across empty space. Maxwell introduced the radical notion that fields themselves are physical entities capable of carrying energy and momentum through space. This concept of a self-sustaining dynamic field was revolutionary, providing a new framework for understanding the interactions of forces and matter. By reconceptualizing forces as properties of space itself, Maxwell changed the way scientists thought about causality, propagation, and the structure of the universe. The field concept became central to all subsequent developments in physics, influencing relativity, quantum field theory, and modern particle physics. Another significant aspect of Maxwell's work was its unification of previously disparate laws of electricity and magnetism. Prior to Maxwell, scientists had observed individual phenomena. Coulomb's law described forces between static charges, Ampere's law quantified magnetic interactions due to currents, and Faraday had demonstrated electromagnetic induction. Maxwell's genius was in recognizing the deep connections among these phenomena and expressing them as a unified, mathematically consistent system. His equations demonstrated that electric and magnetic fields are interdependent and that changes in one induce changes in the other, revealing a dynamic interplay that underlies all electromagnetic interactions. This unification not only explained known observations but also predicted entirely new phenomena, illustrating the explanatory and predictive power of theoretical synthesis. Maxwell's equations also had profound implications for the understanding of energy. He showed that electromagnetic fields carry energy, which can be stored, transmitted, and converted between electric and magnetic forms. This insight led to the concept of energy flux in the form of the Poynting vector, later formalized by John Henry Poynting, which describes the flow of electromagnetic energy through space. Maxwell's understanding of energy in fields bridged the gap between mechanics and electromagnetism, demonstrating that forces and motion could be understood as expressions of energy distribution and transfer. This perspective provided a unifying framework for interpreting a wide range of physical phenomena, from the behavior of circuits to the propagation of light and radiation. The elegance and generality of Maxwell's equations also reflected his aesthetic sensibility. Maxwell pursued formulations that were not only mathematically rigorous, but conceptually clear and harmonious. He sought to capture the underlying symmetry and unity of natural laws, reflecting his belief that the universe is governed by principles of coherence and order. This emphasis on clarity and beauty was not merely philosophical, it was practical, guiding Maxwell to formulations that were general, predictive, and applicable across diverse phenomena. His approach demonstrated that scientific insight often arises from the interplay of technical skill, conceptual understanding, and an appreciation for the inherent structure of nature. Maxwell's unification of electricity, magnetism, and light had immediate and far-reaching technological implications. The recognition that electromagnetic waves propagate through space at a finite speed opened the door to practical applications in communication and energy transmission. Engineers and inventors, building on Maxwell's theoretical framework, developed technologies such as radio transmitters, antennas, and wireless telegraphy. Maxwell's work, though initially abstract and theoretical, thus directly influenced the technological landscape, demonstrating the interplay between fundamental scientific discovery and applied innovation. The impact of his theory extended far beyond the laboratory, shaping the modern world in ways that continue to resonate today. Equally important was Maxwell's influence on subsequent theoretical developments. His conceptualization of fields and waves laid the groundwork for the theories of relativity and quantum mechanics. Albert Einstein later cited the invariance of the speed of light, predicted by Maxwell, as a critical motivation for his special theory of relativity. The field concept became central to quantum electrodynamics and modern particle physics, forming the basis for the understanding of forces and interactions at the most fundamental levels. Maxwell's work thus served as a bridge between classical physics and the revolutionary scientific paradigms of the 20th century, illustrating the enduring significance of his contributions. Maxwell's methodological approach also left a lasting legacy for scientific practice. He demonstrated the importance of integrating observation, experimentation, and theoretical modeling. His careful study of Faraday's experiments, combined with rigorous mathematical formalism, showed that theoretical predictions could guide future experiments and expand the boundaries of knowledge. Maxwell exemplified a model of scientific inquiry in which imagination, discipline, and critical reasoning work in concert, providing a template for generations of physicists. His approach underscored that scientific innovation is not merely the accumulation of data, but the synthesis of understanding, prediction, and conceptual unification. In addition to his theoretical achievements, Maxwell was deeply engaged in communicating his ideas. He published extensively, carefully explaining the physical meaning of his equations and their implications. His writings were notable for clarity, rigor, and conceptual insight, making complex ideas accessible to the scientific community. Maxwell's ability to articulate abstract concepts, relate them to empirical observations, and provide predictive guidance facilitated the acceptance and integration of his work. This combination of innovative thought and clear exposition exemplified the ideal of scientific scholarship, blending discovery with communication. Maxwell's unification of electromagnetism also had philosophical implications, reshaping the understanding of the natural world. By demonstrating that light is an electromagnetic phenomenon and that fields permeate space, he challenged mechanistic views and suggested that the universe is structured by underlying principles that can be expressed mathematically. His work inspired reflection on the nature of causality, space, and time, influencing both scientific and philosophical discourse. Maxwell's vision revealed the interconnectedness of phenomena, showing that seemingly separate observations are aspects of a coherent, unified reality, Maxwell's contributions to physics were also characterized by a commitment to empirical validation. While he relied heavily on mathematical reasoning, he consistently tested his predictions against known phenomena and designed thought experiments to explore the implications of his theory. This balance of abstraction and grounding ensured that his equations were not mere formalism, but reflected the behavior of the natural world. Maxwell's insistence on connecting theory to observation exemplified a rigorous scientific ethic, demonstrating that theoretical innovation must remain anchored in empirical reality. The broader significance of Maxwell's work extends to education, methodology, and the philosophy of science. His ability to synthesize experimental observation, mathematical formalism, and conceptual insight provides a model for how science can advance knowledge. Maxwell's career demonstrates that groundbreaking discoveries often emerge from the careful integration of prior knowledge, imaginative conceptualization, and disciplined reasoning. His work underscores that science progresses not only through incremental observation, but through bold, unifying ideas that transform understanding and open new avenues of inquiry. James Clerk Maxwell's contributions to physics were not confined to electricity and magnetism. He also revolutionized the understanding of light, color, and human perception. From a young age, Maxwell had been fascinated by the nature of light and the spectrum of colors, conducting experiments with prisms and colored materials. His curiosity in this area matured alongside his rigorous education in mathematics and physics, enabling him to approach color and optics with both experimental precision and theoretical insight. Unlike many scientists of his era, who studied light primarily as a wave or a particle phenomenon, Maxwell sought to understand the mechanisms underlying the perception of color and to quantify the relationship between physical light properties and human visual experience. His work in this domain bridged physics, physiology, and psychology, establishing a foundation for modern color science. Maxwell's exploration of color was motivated by questions about how humans perceive and reproduce the wide range of colors in the natural world. He recognized that the visible spectrum, though continuous, could be interpreted through a combination of fundamental color components. Drawing inspiration from the trichromatic theories proposed by Thomas Young and Hermann von Helmholtz, Maxwell sought to mathematically and experimentally verify the idea that all perceivable colors could be produced by blending three primary colors, red, green, and blue. This hypothesis, though conceptually simple, required rigorous experimental confirmation and precise measurement techniques to connect physical stimuli with perceptual outcomes. To investigate the nature of color perception, Maxwell devised ingenious experimental setups. He used colored filters, spinning disks, and controlled light sources to create combinations of red, green, and blue light. By carefully adjusting the intensity of each component and observing the resulting color, Maxwell was able to demonstrate that a wide range of colors could indeed be reproduced from these three primary sources. His experiments were methodical and systematic, emphasizing quantitative measurement alongside qualitative observation. Maxwell's ability to translate abstract hypotheses into reproducible experiments reflected his broader scientific approach, integrating theoretical reasoning with empirical verification. Maxwell's work also extended to the study of color photography, an emerging technology in the 19th century. In 1861, he produced what is now recognized as the first durable color photograph, using a method that applied his trichromatic principles. By photographing a scene 3 times through red, green, and blue filters, and then recombining the images through projection, he created a color image that accurately reproduced the original scene. This achievement was not merely a technical demonstration. It provided concrete evidence for his theoretical understanding of color perception and established a practical application of his research. Maxwell's color photograph remains a landmark in the history of photography and visual science, illustrating the power of combining theory, experimentation, and innovative methodology. In addition to practical applications, Maxwell's research contributed to the understanding of the physics of light itself. He explored the relationships between light intensity, wavelength, and the perception of color, showing how physical properties of light correspond to perceptual experience. By connecting the spectral characteristics of light to human vision, Maxwell laid the groundwork for quantitative colorimetry, the scientific measurement of color. His work enabled subsequent researchers and engineers to develop standardized methods for describing, reproducing, and manipulating color in both scientific and technological contexts. Maxwell also investigated the properties of polarized light, building upon the earlier discoveries of Etienne, Louis Malus, and Augustin Jane Fresnel. Polarization, the orientation of light waves in particular planes, was a phenomenon that revealed deeper aspects of light's wave nature. Maxwell's studies clarified the relationship between polarization, reflection, and refraction, demonstrating that the behavior of polarized light could be predicted and quantified using mathematical models. His experiments with polarization not only advanced theoretical understanding, but also had practical implications for optical instruments, photography, and the study of atmospheric and material properties. A significant aspect of Maxwell's contributions to optics was his integration of experimental observation with theoretical modeling. He was not content merely to catalog phenomena, he sought to explain them through mathematical and physical principles. This approach mirrored his work in electromagnetism, where he had unified disparate observations into a coherent theoretical framework. In optics and color science, Maxwell similarly sought unifying principles, connecting the physical properties of light to the physiological mechanisms of human vision. His work demonstrated that understanding perception requires both quantitative measurement and conceptual analysis, anticipating modern approaches in vision science, imaging technology, and color engineering. Maxwell's contributions to color theory and optics also had long-lasting technological impact. By establishing that all colors could be reproduced through combinations of three primary lights, he provided the conceptual foundation for modern color displays, television, and digital imaging. The RGB's red, green, blue color model used universally in electronic displays, photography, and printing directly reflects Maxwell's insights into the trichromatic nature of vision. His work bridged pure scientific inquiry and practical application, illustrating how fundamental research can drive innovation across multiple domains. Moreover, Maxwell's exploration of light and color reinforced the broader significance of his scientific philosophy. He approached natural phenomena as systems governed by coherent laws, seeking underlying principles that unify diverse observations. In color and optics, this philosophy led him to bridge physics, physiology, and technology, demonstrating that scientific understanding is most powerful when it integrates multiple perspectives. Maxwell's work showed that even everyday phenomena, like the perception of color, can be analyzed rigorously, quantified precisely, and applied creatively. In addition to color, Maxwell contributed to the study of diffraction, interference, and other optical phenomena, further solidifying his reputation as a pioneering physicist. He applied mathematical methods to predict patterns of light behavior, tested his predictions experimentally, and developed instruments and techniques to measure and visualize optical effects. His work in this area not only expanded the understanding of light as a physical wave, but also demonstrated the applicability of theoretical physics to practical problems, from instrument design to visual representation. Maxwell's legacy in optics and color science is a testament to his comprehensive scientific vision. He demonstrated that human perception, physical properties of light, and technological applications can be understood within a unified framework. By combining careful experimentation, rigorous mathematical reasoning, and imaginative conceptualization, he advanced knowledge in ways that continue to shape modern science. His color photograph, his trichromatic theory, and his studies of polarized and diffracted light exemplify a methodology that integrates observation, theory, and innovation, serving as a model for generations of scientists and engineers. Ultimately, Maxwell's work in color and optics illustrates the breadth of his genius. While his contributions to electromagnetism transformed theoretical physics, his insights into light and color transformed the understanding of perception and visual representation. By bridging theory and practice, physics and physiology, Maxwell created a legacy that spans both fundamental science and technological application. His approach demonstrates that profound scientific achievement often arises from the integration of curiosity, rigor, and creativity, revealing the hidden structures of the world and enabling practical innovations that enrich human experience. James Clerk Maxwell's contributions to physics extended far beyond electromagnetism and optics, reaching into the microscopic world of gases and the statistical behavior of particles. During the mid-19th century, the behavior of gases presented a profound challenge to physicists. The laws of thermodynamics had been formulated, describing the relationships between heat, work, and energy, but the microscopic mechanisms underlying these phenomena remained obscure. Maxwell's insight was to apply mathematical reasoning to the motion of individual particles, bridging the gap between the observable properties of gases and the unseen molecular activity that produced them. His work in kinetic theory laid the foundation for statistical mechanics, transforming the understanding of matter at a fundamental level. The study of gases had long been guided by empirical laws, such as Boyle's law, Charles's law, and Gay-Lussac's observations relating pressure, volume, and temperature. While these relationships were experimentally verified, they did not explain why gases behaved in such predictable ways. Maxwell's approach was revolutionary in its simplicity and ambition. He sought to explain the macroscopic properties of gases by considering the microscopic motions of molecules. He reasoned that pressure arises from the collisions of countless particles with the walls of a container, that temperature reflects the average kinetic energy of these particles, and that the collective behavior of molecules produces the measurable properties of gases. This insight transformed the study of thermodynamics from a purely phenomenological science into a theoretical discipline grounded in molecular dynamics. Central to Maxwell's approach was the use of probability and statistics to describe the behavior of large numbers of particles. He recognized that it is impossible to track the motion of every individual molecule in a gas, yet the aggregate behavior could be understood through statistical laws. Maxwell introduced the concept of a velocity distribution, a mathematical function describing the probability that a particle has a given speed at a particular temperature. This idea, later formalized as the Maxwell-Boltzmann distribution, provided a quantitative framework for predicting the range of particle velocities in a gas and their contribution to macroscopic properties such as pressure and temperature. By linking microscopic dynamics to observable thermodynamic quantities, Maxwell created a bridge between theory and experiment that was both elegant and predictive. Maxwell's work in kinetic theory also emphasized the importance of assumptions and idealizations in scientific modeling. He considered ideal gases, composed of perfectly elastic, non-interacting particles, as a starting point for understanding more complex behavior. By analyzing collisions, momentum transfer, and energy distribution within this idealized framework, he derived results that matched experimental observations with remarkable accuracy. These idealizations allowed him to uncover general principles that apply to real gases under a wide range of conditions, demonstrating the power of abstraction in uncovering the fundamental mechanisms governing natural phenomena. A significant consequence of Maxwell's theory was the recognition that temperature and molecular motion are intimately connected. He showed that the average kinetic energy of molecules is proportional to the temperature of the gas, providing a microscopic interpretation of thermodynamic concepts. This insight clarified the nature of heat as energy associated with molecular motion, rather than as a mysterious fluid or substance, as was once believed. Maxwell's treatment of gases thus contributed directly to the modern understanding of energy, motion, and the statistical basis of thermodynamics. Maxwell's kinetic theory also paved the way for the concept of statistical mechanics, developed further by Ludwig Boltzmann. By emphasizing the probabilistic behavior of large ensembles of particles, Maxwell showed that macroscopic regularities emerge from microscopic randomness. This perspective challenged deterministic views of nature, suggesting that the laws of probability govern the behavior of systems composed of vast numbers of interacting components. Maxwell's insight that order can arise from statistical regularity laid the foundation for later developments in physics, from quantum mechanics to chaos theory, and remains central to the study of complex systems today. In addition to theoretical contributions, Maxwell conducted experiments and thought experiments that clarified the implications of his theory. He considered questions about energy distribution, molecular collisions, and the behavior of gases under different conditions. Using these explorations to refine his models, his analysis revealed subtle phenomena, such as the distribution of molecular speeds and the effects of mass and temperature on particle motion. These insights not only deepened understanding of gases, but also illustrated the broader principle that seemingly simple systems can exhibit rich and predictable behavior when analyzed through the lens of mathematics and probability. Maxwell's work in kinetic theory also influenced the understanding of diffusion, viscosity, and thermal conductivity in gases. By linking these macroscopic phenomena to molecular motion, he provided a coherent framework that explained a wide range of observations. For example, he showed how the random motion of molecules leads to the diffusion of particles and the transfer of heat, demonstrating that transport properties arise naturally from microscopic dynamics. This unification of theory and experiment exemplifies Maxwell's approach to physics, in which mathematical reasoning, conceptual insight, and empirical evidence are integrated to produce a comprehensive understanding of natural phenomena. Moreover, Maxwell's statistical treatment of gases introduced the concept of fluctuations, recognizing that quantities such as pressure and energy vary microscopically around average values. This recognition of variability at the molecular level anticipated later developments in statistical physics and thermodynamics, including the study of fluctuations in small systems and the probabilistic interpretation of entropy. Maxwell's insights revealed that macroscopic stability and predictability emerge from the collective behavior of countless individual components, providing a framework for understanding complex systems in physics, chemistry, and beyond. Maxwell's contributions to kinetic theory also demonstrated the power of mathematical modeling in physics. By constructing equations that described particle motion, energy distribution, and probability, he created predictive tools that could be tested against experiment. His work showed that mathematics is not merely a descriptive language, but a means of discovering and formalizing fundamental principles. The success of Maxwell's models in capturing the behavior of gases reinforced the idea that physical reality can be understood through abstract reasoning, quantitative analysis, and rigorous logical deduction. Importantly, Maxwell's work in this area was interconnected with his broader contributions to physics. The methods he developed for analyzing large systems of particles informed his approach to electromagnetic fields, waves, and radiation. His understanding of statistical behavior and energy transfer helped him conceptualize the propagation of light as an electromagnetic wave, linking microscopic dynamics to macroscopic observables in multiple domains. Maxwell's ability to synthesize ideas across areas of physics exemplifies his holistic approach, in which discoveries in one field illuminate and enrich understanding in another. Maxwell's kinetic theory also had practical implications, influencing engineering, chemistry, and later developments in statistical mechanics. His insights guided the design of experiments, the interpretation of thermodynamic measurements, and the prediction of gas behavior under varying conditions. The Maxwell-Boltzmann distribution became a cornerstone of chemical physics and physical chemistry, enabling calculations of reaction rates, diffusion constants, and thermal properties. In this way, Maxwell's theoretical work translated directly into tools for scientific and technological advancement. Through his pioneering research on gases and statistical mechanics, Maxwell demonstrated the profound power of combining imagination, mathematics, and empirical reasoning. He revealed that microscopic motion, when analyzed systematically, can explain the macroscopic regularities of nature. His work exemplified the integration of theory and experiment, abstraction and observation, and individual insight and cumulative scientific knowledge. Maxwell's contributions to kinetic theory remain a foundational element of modern physics, highlighting his ability to uncover deep principles underlying the natural world and to connect them to observable reality. Ultimately, Maxwell's work in the kinetic theory of gases illustrates his genius for unifying diverse phenomena, applying mathematical reasoning to complex systems, and revealing the hidden structures that govern natural behavior. By elucidating the statistical nature of molecular motion, he transformed thermodynamics, laid the groundwork for statistical mechanics, and provided a model for the systematic exploration of the physical universe. His legacy in this field continues to influence research in physics, chemistry, and engineering, demonstrating the enduring significance of his insights and the breadth of his scientific vision. James Clerk Maxwell's groundbreaking work in electromagnetism not only transformed theoretical physics, but also laid the foundation for a technological revolution that continues to shape the modern world. By unifying electricity, magnetism, and light into a single coherent framework, Maxwell provided a conceptual structure that enabled future generations to harness electromagnetic phenomena for practical purposes. The predictive power of his equations allowed scientists and engineers to explore technologies that had previously been unimaginable, ranging from wireless communication to electrical power distribution. Maxwell's theoretical insights became the blueprint for innovations that redefined industry, communication, and everyday life. The predictive nature of Maxwell's electromagnetic theory was one of its most remarkable aspects. By demonstrating that electric and magnetic fields could propagate as waves through space at a finite speed, Maxwell revealed that these waves could carry energy and information over long distances. This theoretical prediction directly anticipated the development of radio waves and wireless communication. Decades after Maxwell formulated his equations, Heinrich Hertz experimentally confirmed the existence of electromagnetic waves, validating Maxwell's predictions and opening the door to the invention of radio. The work of pioneers such as Guglielmo Marconi and Nikola Tesla built directly upon Maxwell's theoretical framework, translating abstract equations into devices capable of transmitting signals across continents and oceans. Maxwell's equations also enabled the development of electrical engineering as a rigorous discipline. By providing a clear and predictive understanding of how electric and magnetic fields interact, his theory allowed engineers to design circuits, transformers, and motors with greater precision and efficiency. The generation, transmission, and utilization of electrical power became systematically understandable, facilitating the electrification of cities, industries, and homes. The theoretical foundations laid by Maxwell ensured that electrical technology could move beyond trial and error experimentation, providing a principled approach to designing complex systems that rely on electromagnetic principles. In addition to electrical power and communication, Maxwell's theory profoundly influenced optics and photonics. By showing that light is an electromagnetic wave, he unified the fields of optics and electromagnetism, providing a theoretical framework for understanding lenses, mirrors, diffraction, and polarization in terms of fundamental physical laws. This unification enabled the development of optical instruments, lasers, fiber optic communication, and imaging technologies, all of which rely on the precise control of electromagnetic waves. Maxwell's insights transformed light from a mysterious phenomenon into a quantifiable, manipulable aspect of the physical world, fueling advances in science, medicine, and technology. Maxwell's impact on the technological revolution was further amplified by the way his work informed telecommunications. Understanding electromagnetic wave propagation allowed engineers to predict how signals travel through different media, reflect from surfaces, and attenuate over distance. These principles underpin radio, television, radar, and modern wireless networks, including cellular communication and Wi-Fi. Maxwell's equations provided the theoretical foundation that guided the design of antennas, transmitters, and receivers, enabling the global communication networks that define contemporary society. Without Maxwell's conceptual breakthroughs, the rapid development of telecommunications in the 20th century would have been impossible. Another area profoundly affected by Maxwell's work was the field of electronics. His equations clarified the behavior of alternating and direct currents, electromagnetic induction, and resonance phenomena. Understanding these interactions allowed inventors to develop electric generators, transformers, and motors with unprecedented efficiency and reliability. The Industrial Revolution of electricity, powering factories, homes, and public infrastructure, was made feasible through the principles Maxwell had articulated decades earlier. In this sense, Maxwell's theoretical contributions directly fueled the material and technological growth of modern civilization. Maxwell's influence extended to the understanding and development of electromagnetic waves in vacuum and dielectric media, which underlies radio, television broadcasting, and satellite communication. Engineers could calculate wavelengths, frequencies, and propagation characteristics using his formulas, enabling long-distance communication and space exploration. The principles of waveguides, antennas, and signal modulation all rest on the predictive capacity of Maxwell's equations. In essence, the global communication networks and technologies that permeate contemporary life are built upon his theoretical vision. The impact of Maxwell's work was not limited to immediate technological applications. It also inspired further scientific revolutions. Albert Einstein, for instance, cited Maxwell's equations as a key motivation for the special theory of relativity. The realization that electromagnetic waves propagate at a constant speed, independent of the motion of the observer, challenged classical notions of space and time. Maxwell's work thus indirectly transformed our understanding of the fundamental structure of the universe, influencing both theoretical physics and the practical technologies that depend on these principles, including GPS, satellite navigation, and relativistic communication systems. Maxwell's integration of theory and practice exemplified a model for scientific innovation that combined rigorous mathematics, physical intuition, and practical relevance. By demonstrating that abstract theoretical principles could predict and explain phenomena with tangible technological applications, Maxwell bridged the gap between pure science and engineering. His work illustrated how deep theoretical insight could drive applied innovation, a principle that continues to guide scientific and technological advancement in the modern era. The electrification of society, the development of wireless communication, and the ability to manipulate electromagnetic waves in diverse applications all trace their origins to Maxwell's equations. His work provided a roadmap for inventors, engineers, and scientists to harness nature's invisible forces, transforming human capability and daily life. From transmitting messages across continents to lighting homes and powering industries, Maxwell's theoretical insights became the engine of a technological transformation whose effects continue to expand. Maxwell's impact also includes contributions to measurement and standardization in electrical engineering. By providing a clear understanding of electromagnetic interactions, his theory allowed the establishment of standardized units, precise calibration methods, and predictable behavior of electrical systems. This standardization was critical for the reliable deployment of large-scale technologies such as power grids, telecommunications networks, and industrial machinery. Maxwell's influence ensured that technological progress could be systematic, reproducible, and scalable, avoiding the limitations of ad hoc engineering approaches. Beyond specific technologies, Maxwell's work inspired a broader cultural and intellectual shift. The concept that nature could be described through unified, predictive laws encouraged a generation of scientists and engineers to seek underlying principles across disciplines. Maxwell's success demonstrated that abstract theoretical work could produce concrete, transformative outcomes, fostering a culture of innovation in both research and industry. His contributions exemplify the interplay between scientific discovery and societal progress, showing how fundamental understanding can catalyze profound technological and cultural change. Maxwell's legacy in driving the technological revolution illustrates the enduring power of ideas. While many technological advances rely on incremental engineering, Maxwell's theoretical insights enabled leaps in capability that reshaped human experience. Wireless communication, electrical power distribution, modern optics, and a host of contemporary technologies trace their lineage to his equations. By revealing the principles underlying electromagnetic phenomena, Maxwell empowered humanity to manipulate and control forces that were previously invisible and poorly understood, ushering in an era defined by connectivity, energy, and innovation. In summary, James Clerk Maxwell's impact on electromagnetic theory was inseparable from the technological revolution it enabled. His unification of electricity, magnetism, and light provided a predictive framework that guided scientific discovery, engineering innovation, and technological deployment. From radio waves to electrical grids, from optical devices to communication satellites, Maxwell's work transformed both the understanding of the physical world and the human capacity to harness it. His vision exemplifies the power of theoretical insight to shape practical reality, demonstrating how the intellect of a single individual can trigger advancements that continue to define modern civilization. James Clerk Maxwell's legacy in physics is monumental, encompassing theoretical breakthroughs, experimental innovations, and a profound influence on the development of modern science. His work transformed not only the understanding of electromagnetism, light, and gases but also the very framework within which scientists approach the natural world. Maxwell's ability to unify disparate phenomena under comprehensive mathematical principles established him as one of the greatest scientific minds of the 19th century, and his influence continues to resonate across physics, engineering, and technology. At the core of Maxwell's legacy is his conceptual innovation, the unification of electricity, magnetism, and light. Prior to Maxwell, these domains were studied largely in isolation, with little recognition of their interrelated nature. Maxwell demonstrated that all electromagnetic phenomena could be described by a single, coherent set of equations, revealing the underlying harmony of physical laws. This unification was not only mathematically elegant, but also profoundly explanatory, predicting behaviors that had not yet been observed and providing the theoretical foundation for future discoveries. By showing that light is an electromagnetic wave, Maxwell bridged the gap between optical science and electromagnetic theory, transforming the understanding of the physical world and influencing generations of physicists who would follow. Maxwell's work also exemplifies the power of theoretical insight in advancing scientific knowledge. His equations predicted electromagnetic waves decades before they were experimentally detected, illustrating the capacity of rigorous reasoning to anticipate phenomena beyond the reach of contemporary observation. Heinrich Hertz's later confirmation of these waves validated Maxwell's theory and opened a new era of experimental and technological exploration. This predictive power, coupled with empirical verification, established a model for scientific progress in which theory and experiment are mutually reinforcing, highlighting the importance of mathematical modeling in understanding natural phenomena. In addition to electromagnetism, Maxwell's contributions to the kinetic theory of gases demonstrated his ability to connect microscopic behavior with macroscopic observations. By describing gases in terms of molecular motion and probability, Maxwell provided a statistical framework that explained temperature, pressure, and other thermodynamic properties. His work laid the foundation for statistical mechanics, enabling later physicists such as Ludwig Boltzmann and Josiah Willard Gibbs to develop a deeper understanding of matter, energy, and entropy. Maxwell's approach showed that order and predictability in physical systems emerge from the collective behavior of countless individual particles, a principle that remains central to modern physics and complex systems theory. Maxwell's contributions to color theory and optics further illustrate the breadth of his scientific vision. By demonstrating that all perceivable colors could be produced through combinations of three primary colors, and by creating the first durable color photograph, he bridged the gap between theoretical physics and human perception. His work in this domain influenced the development of modern imaging, display technologies, and color reproduction standards, demonstrating the practical impact of fundamental scientific insight. Maxwell's ability to integrate physics, physiology, and technology exemplifies his holistic approach to science, in which diverse domains are connected through fundamental principles. Beyond specific scientific achievements, Maxwell's methodology has had a lasting impact on the practice of physics. He combined rigorous mathematical formalism with deep physical intuition and careful experimental validation. His ability to translate qualitative observations into quantitative laws set a precedent for modern theoretical physics, emphasizing the importance of coherence, predictive power, and empirical grounding. Maxwell's approach demonstrates that breakthroughs often arise from the synthesis of abstract reasoning, imaginative insight, and systematic experimentation, providing a model for scientific inquiry that remains influential today. Maxwell's influence also extends to the conceptual foundations of modern physics. His field theory introduced the idea that forces are mediated through space by dynamic fields, rather than acting instantaneously at a distance. This conceptual shift paved the way for Einstein's theories of relativity, which rely on the finite propagation of interactions, and for the development of quantum field theory, which describes fundamental particles and forces in terms of underlying fields. By reimagining the nature of interaction and causality, Maxwell reshaped the conceptual landscape of physics, influencing the theoretical frameworks that define contemporary understanding of the universe. Technologically, Maxwell's legacy is ubiquitous. His theoretical insights underlie nearly all modern electrical, optical, and communication technologies, from power grids and motors to radios, television, fiber, optic networks, and wireless communication. Maxwell's equations provide the foundation upon which these systems operate. Engineers and inventors have relied on his predictive framework to design and optimize devices, demonstrating the profound practical impact of his work. The technological revolution of the late 19th and 20th centuries and the ongoing evolution of digital and communication systems owe much to Maxwell's theoretical vision. Maxwell's influence on the scientific community was also amplified by his ability to communicate complex ideas clearly and effectively. His writings were marked by precision, clarity, and careful reasoning, making difficult concepts accessible to both contemporaries and future generations. By articulating his theories with rigor and insight, Maxwell ensured that his work could be studied, tested, and expanded upon, allowing subsequent scientists to build upon his foundations. This combination of intellectual brilliance and communicative skill contributed to the enduring impact of his legacy. The philosophical dimension of Maxwell's work is equally significant. His belief in the unity and harmony of natural laws inspired a broader scientific vision, in which seemingly disparate phenomena could be explained through fundamental principles. Maxwell's holistic approach demonstrated that understanding the universe requires both abstraction and attention to empirical detail, and that the search for underlying laws is as much an intellectual endeavor as it is a practical one. His perspective encouraged a culture of inquiry in which curiosity, creativity, and rigor are intertwined, influencing not only physics but the philosophy of science itself. Maxwell's legacy also resides in the inspiration he provided to future generations of scientists. Albert Einstein, Hendrik Lorentz, and countless others drew upon Maxwell's equations to develop relativity, quantum theory, and modern electrodynamics. Maxwell's demonstration of the predictive power of theory, combined with careful experimental grounding, became a guiding principle for physicists exploring realms from the subatomic to the cosmological. His work exemplifies how a single individual, through intellectual rigor and imaginative insight, can shape the trajectory of an entire scientific discipline. Ultimately, Maxwell's enduring influence is reflected in both the content and methodology of modern physics. He transformed understanding of electromagnetic forces, light gases, and statistical behavior. He provided theoretical tools that guide technology and innovation, and he exemplified a model of scientific reasoning that integrates mathematics, experiment, and conceptual insight. Maxwell's vision extended beyond the boundaries of his time, uniting diverse domains of knowledge and revealing the coherence and elegance underlying the natural world. In sum, James Clerk Maxwell's contributions transcend individual discoveries, representing a paradigm shift in how nature is understood, analyzed, and harnessed. His unification of electromagnetism, insight into molecular motion, exploration of light and color, and methodological rigor collectively transformed physics and science as a whole. Maxwell's work demonstrates the enduring power of theoretical insight, the importance of bridging theory and experiment, and the capacity of a single mind to illuminate the fundamental laws that govern the universe. His legacy continues to shape the scientific, technological, and intellectual landscape, securing his place as one of the most influential figures in the history of human knowledge.